Hi everybody, this is David Paul. We're here today to talk about an emerging technology for water and wastewater minimization. That's membrane capacitive deionization. So it'll be a 40-minute presentation. I'll give a brief intro here, and then Bryan from VOLTEA will provide the details. And we hope to be finished to where we can have 15 to 20 minutes of Q&A. So at any time, type your questions into the question box, and then we'll cover the question and answers at the end. So this presentation is recorded, so tomorrow or the next day you'll be able to go on our website, and if you want to view it again, or if somebody else wants to view it, they can do that. You'll also receive a thank you email tomorrow or the next day, and it'll have a PDF of this presentation, so you won't have to take a lot of notes. Just listen and learn as much as you can on this. So just so you're aware, we have no financial relationships with VOLTEA. We are not endorsing VOLTEA. We're not endorsing MCDI. So this is just something that we think is of interest. It's an emerging technology, and we're interested in it. We want to learn about it, so we've invited VOLTEA to come and give a presentation today. So I have about 40 years of experience in high-tech water treatment. I don't have any experience with the MCDI. So Bryan does. So he's been the CEO of VOLTEA since 2014, and he's got a really good background, both with GE and has a PhD in polymer science. So I'm going to give just a really brief intro for water and wastewater minimization, and also just a little bit on MCDI. So water and wastewater costs. This is a huge issue today, especially if you're on city water and sewer water. The charges can be extraordinary. So if we can reduce water in or wastewater out, or reduce power consumption, that can be just a huge cost savings. And that's why we look at these new technologies, because we're looking for ways of achieving high recovery rates at hopefully less cost than we're paying today. So that less cost could be reduced power, and that could be either from efficient operation or a new technology, and that's what we're talking about today, a newer technology. So just to look at the membrane technologies today, we have microfiltration and ultrafiltration, and those can be either polymeric or ceramic. We have nanofiltration and reverse osmosis membrane systems. We have electrical potential-driven membrane technologies like electrodialysis reversal, electrodeionization, and the one that we're going to talk about today, membrane capacitive deionization. A couple of others, membrane technologies today, forward osmosis and membrane distillation. Of those technologies, reverse osmosis has been around 40 years. It's current. It's a proven technology. So is membrane filtration. So is electrodialysis reversal. As far as emerging membrane technologies, ones that we have done a webinar on closed circuit desalination. In the future, we'll have one on forward osmosis and another one on membrane distillation. And today is on MCDI. As we're looking at these new technologies, and they come out all the time now. Matter of fact, if you look at today's What's New in Advanced Water Treatment, that's our weekly e-newsletter that goes out every Wednesday, you'll see that there's a claim from the UK that they have a new membrane that is just going to solve the world's water problems. Well, you'll hear this come out at least 4 times a year. So lots of new membrane technologies. What we have to do is really analyze these new technologies. And the things that we're really taking a look at is we want to know real world capital cost, operating cost, and operations. We want to know, are they prone to scaling? Are they prone to fouling? And how do we handle those? So these are things that I'm going to be listening for in today's presentation by Bryan, just to to see what MCDI is like. So scaling, I think another important thing as you're analyzing emerging technologies is in the technical or marketing literature, you may see things like, well, this technology can operate at 350,000 TDS. Well, that's probably 350,000 TDS of sodium chloride, not 350,000 TDS of anything. Because essentially, where scaling occurs, the 100% saturation point, where that occurs, is basically going to occur if the water is concentrated by any technology. So once you hit 100% saturation, you can go a little bit past that, but not necessarily a lot past that without doing things like injecting scale inhibitors. So here's just a list different scaling compounds, calcium sulfate, barium sulfate, and what you would find in like an RO concentrate stream. Well, again, in these emerging technologies, we want to see what they can do as far as scaling and how they can handle fouling. So there are lots of different fouling particles and organic material and slimy, sticky, polymeric type substances that can foul different technologies. And we need to know with these emerging technologies, how do they really act on real water? And can we clean them? So if they scale or if they foul, how do we clean them? So again, when we're evaluating emerging technologies, we really want to see what's available. Are we talking about just laboratory benchtop type of data, or do we actually have full scale, maybe even hundreds of gallons per minute systems? So again, that's the type of things that I'll be looking at today. And then the real world operations. What can we expect with this? And then the real world cost. And then I've just got 5 quick slides because the whole rest of the presentation is going to be on the details. But there's capacitive deionization, CapDI, and there's membrane capacitive deionization. Lots of research has gone into creating these cathode and anode materials that will adsorb the ion. So the actual electrode, the cathode and electrode, attract the ions from the feed water, and these adsorb to the electrode material. So here we're seeing a picture of a cathode and an anode, and we see the cations are attracted to the cathode and the anions are attracted to the anode. And once these things get filled up, so once the electrodes get filled with cations and anions, then we have to regenerate them. So regeneration is simply let's alternate the current. So now the cathode becomes the anode, so all the cations are repulsed and they're driven into the waste stream. Well, at this same time, with capacitive deionization, the same time that we're desorbing the cations, we're also attracting or adsorbing the anions during regeneration. So that's the real claim to fame of membrane capacitive deionization, is we put a cation transport membrane, anion transport membrane around the electrode or cathode and anode material. So now when regeneration occurs, it's only occurring one way. So the cations will all pass out and go into the waste stream, but the anions can't pass through a cation transport membrane. So it's an improvement over the CDI technology. All right, so that's just a brief introduction, And now I'd like to turn it over to Bryan, and he will give the balance of the presentation, and then I'll come back at the beginning of the Q&A.
Okay. David, thank you for that introduction. And I'd like to thank all of the participants that have dialed in for your participation and for your time today as well. I'm going to, I've structured this presentation to largely be engineering based. And what I mean by that is it's not so much a commercial presentation. This is based on real world data. Towards the end of the presentation, we're going to talk through 7 different case studies. These are different applications in different industries. And David mentioned something in his opening remarks that is actually near and dear to my heart. I did once upon a time earn a PhD, and so I have a great appreciation for fundamental research and academic research. However, I have spent the entirety of my career trying to reduce that fundamental research to the real world, because my sense has always been that we shouldn't be doing research simply for the sake of doing research. If we can't figure out how to make mankind's lives better, how to be better stewards of the planet, then what's the point of the research? And so I've always been very highly applied in my appreciation for advanced research and development, and that's how I'm going to structure our discussion today. So if we go forward just one page, why is Voltea driven to innovate? And the answer to this question is, having built and operated 2 businesses based on reverse osmosis, one inside GE Water and one as a founding member of 7 Seas Water, a company that I am ultimately proud of, I believe that there is a fundamentally better way, a lower cost way, for us to desalinate and soften water. And so we are working tirelessly to drive what we think is a revolutionary, cost-effective technology with greater environmental responsibility into every business and every home on this planet. And so that's why I and my staff come to work every day. We've got offices in Sassenheim, Netherlands, and also an advanced manufacturing facility in Dallas, Texas. And I can tell you that the near 40 employees worldwide at Voltea come to work every day because we fundamentally believe there's a better way to soften and desalinate water. So if we go forward one page, I'm on a page titled Voltea's Membrane CapDI. David described it. I'm going to give you a little bit different look at it, but Voltea scientists were the first around the world to recognize and patent the concept of using ion exchange membranes on each of the electrode surfaces. In actual fact, Voltea was a spin-out from Unilever, and at the same time that Voltea scientists were working on this, an incredibly brilliant gentleman by the name of Mark Andelman was also working on this technology through a company called BioSource in Massachusetts of the United States. And after a couple of years, BioSource and Voltea merged. The fundamental idea was exactly as David described. If you have 2 electrode surfaces and you apply a direct current potential to each, when you flow water between those 2 surfaces, oppositely charged dissolved salt molecules will, through electrostatic attraction, attract to the oppositely charged electrode surface. And purified or desalinated water will flow out the other side. Now, we're going to talk in a little more detail in a minute, but fundamentally, you can very easily and intuitively grasp the idea that this is really just electrodialysis. And so the clever bit is the addition of those selective ion exchange membranes, because once the surface of each electrode becomes saturated with dissolved salt molecules, the ability of that electrode to take additional salt out of the water is compromised, and so you need to clean those salts off that electrode surface. We do that at Voltea simply by reversing the polarity of the direct current charge applied to each electrode. And when we do that, of course, the salt molecules are immediately ejected from the surface, but they can't jump across to the other side because of the presence of that ion exchange membrane or ion exchange coating. And so that allows a very elegant way of trapping those dissolved salts in the flow channel, and they can be rinsed away. And so our membrane CapDI systems, over the course of an operating day or an operating month or operating year, are constantly switching back and forth between the first step, which we define as purify, and the second step, which we define as regenerate. Now, a couple things to note are, first of all, we typically operate at a voltage less than 1.5 volts DC. So it's very, very low voltage operation. The second thing to note is that when we go into the regenerate mode, at the same time, we significantly drop the flow rate. So during purify, on average, the flow rate will be about 8 to 10 times higher than it is during regenerate. And it's in this way that we're able to get such a high first pass recovery without having to play engineering games like a second pass or a second stage or something of that nature. So if we go forward one page, I thought I'd give you a little different look how we take this concept from an individual cell pair of electrodes up to a practical device that can function in the real world. And so I'm on the page titled Advanced Materials Science for DESAL. And basically what we do inside is we take literally hundreds of pairs of these electrodes, like I described on the previous page and like what's described in the red dashed box on the left side of this page, and we stack them together in a sandwich fashion. Once we have that sandwiched architecture put together, we take the combination of, and we call those stacks, we take those stacks and we put them inside a housing or pressure vessel. Now, one thing that's important to note about the way we approach our module design is the flow pattern is always outside in. So if you look at the module on the right-hand side in light blue, you'll notice that there's actually two inlets to either side of the housing. And then there's a third outlet in the very middle of the housing. Water always flows into the module through those two ports to either side of the module. It flows across each electrode or each cell pair surface into a flow channel in the center, and it exits the module through that center flow channel. So if we can go forward one page, over the last 2 years in particular, Voltea has made a tremendous amount of progress in taking the cost out of this technology. And so I just wanted to give the audience here a flavor for how we've done that, because as David mentioned in his opening remarks, both the academic and the industrial research literature has increased literally orders of magnitude over the last decade around capacitive deionization and membrane capacitive deionization because of the theoretical potential it has to be a lower cost way to desal or soften water. But the challenge has been its cost structure. And so as we sit here today, Voltea has figured out how to mass produce the components shown on the left-hand side, and that's actually, quite literally, a roll of one of our electrode materials. We then take those components that are produced in large scale, and we convert them into the stacks that are shown in that second picture. This is all done today at an advanced manufacturing facility in Dallas, Texas, via robot. So robotic assembly allowed us to significantly reduce the cost associated with building those stacks, and at the same time, it allows much better reproducibility in terms of stack quality. Those stacks are put inside modules, and I just want to make one comment about the module. The taller industrial commercial module, that's a little bit taller than knee-high on an adult. But we've also miniaturized these modules, and that's a picture of one is shown entitled Consumer Appliance. To give you an idea of scale, that module is about the size of an iPad, maybe 2 iPads sitting on top of each other. So the modules then are put onto what we call a system, and that system is all of the piping and the pumps and the electronics that are required in order to desalinate water in the real world. So the key here is mass production and automated production have been a big part of our strategy to drive cost out, to make both, particularly the capital expense, affordable in the real world for practical applications. So if we can go forward one page, I thought it would be very helpful to just take a minute and describe for people exactly how capacitive deionization compares to traditional desal technologies like reverse osmosis and like EDR. So on the left-hand side of the page, what we've done is we've built a graphic showing the inside on one half of a capacitive deionization module, and on the other side, the inside of an RO, of the RO membranes inside of RO pressure vessel. So the key difference between the two is, for capacitive deionization, water flows unimpeded between two electrode surfaces that are oppositely charged, and we take advantage of electrostatic attraction to remove dissolved salts. Contrast that with reverse osmosis, where literally water is forced mechanically across a membrane surface in order to separate the dissolved salts. And so in the case of reverse osmosis, you rely on high pressure to mechanically force the water over a membrane, whereas capacitive deionization operates at much, much, much lower pressure. Typically, our operating pressure is less than 50 psi, as an example. And lower operating pressure equals lower cost. But in addition to that, capacitive deionization, because of this unimpeded flow channel between the electrode cell pairs, also provides a significantly reduced tendency towards fouling, whether that fouling is in the form of biofouling or scale formation. And the beauty of it is, capacitive deionization, our membranes and electrodes, are resistant to hypochlorite dosing as high as 20 ppm. So in the event that you have a biofouling situation arise, it's very, very easy to cure that with a shock chlorination to kill the biofouling and remove it from the module and return to normal operating conditions. If, on the other hand, you have a fouling issue related to scaling, because as David said, depending on the water type that you're treating, you could have scale-forming molecules like calcium carbonate, magnesium are the biggest culprits, in addition to soft salts like sodium chloride. And so if a scaling issue should arise inside the modules, it's very simply cleaned, and we do it at VOLTEA with a citric acid dosing. So a good dosing of the modules with a sufficient amount of citric acid to get the pH around 2 will clean any scale from the flow channels, and then the modules can return to normal operation. So some very significant key differences in terms of operating costs and in terms of how easy it is to clean the modules and return them to a normal operating condition. In addition to that, there are significant implications around the required pretreatment. So capacitive deionization lends itself readily to much greater swings in the purity of the feed water to the modules. And even if you get into an upset condition of fouling, whether it's biofouling or scale formation, it's very easily cleaned and returned to normal operation. On the right-hand side of the page, I thought what would be very helpful is to compare CapDI to EDR. In terms of operation, these two technologies are very, very similar. And in actual fact, certainly through the 90s and early 2000s, a company by the name of Ionic, which was ultimately acquired by GE Water, was far and away the world's leader in developing and commercializing EDR. In terms of operation, they're very, very similar. The key difference is, in an EDR stack, you have successively alternating pairs of ion exchange membranes with a spacer in between. But you only have one set of electrodes at either end of the EDR stack. And as a consequence, in order to create enough of an electrical potential difference in the middle of the stack to effectively desalinate, EDR devices are typically operated at a significantly higher voltage than we operate CapDI. And the reason for that is, rather than having one pair of electrodes through which we drive voltage, a CapDI module literally has hundreds of pairs of electrodes through the module. And so, as a result, the typical voltage is less than 1.5. And in actual fact, in most all of our applications, we normally don't see an operating voltage any less than 0.5. By the time the voltage gets up to 1.5, we use that as an indicator that that module is approaching the end of its life cycle. And so that's a comparison between traditional DESAL technologies, such as RO and EDR. So if we go forward one page then, why in the world would anybody want to use CapDI? Well, it's an elegant electrical method of softening and generally desalinating water. It allows for a much lower operating cost, and it enables a very wide range of uses with relatively minimal required prefiltration. So we take advantage of electrostatic attraction to remove salt from water using electrical fields. We've achieved a cost structure that makes it capital efficient. It's very energy efficient. We're able to drive very high water recoveries, in some cases as high as 92%. It doesn't require any kind of chemicals or salt. So when you think about the technology as a water softener, you don't have to add non-native salt to get it to function like you do with a traditional ion exchange-based water softener, but you also don't have to use harsh chemicals in order to clean it and return it to a normal operating condition in the event that there's an upset. And so there's some very clear benefits compared to traditional DESAL type technologies or water softening technologies. Now, I do want to comment here that VOLTEA only focuses on brackish water. And the way we define brackish water is where the salinity level is ideally no higher than 3,000 ppm. Now, we do have applications where we've gone a little bit higher than that, as high as 4,000 ppm. But really, that's the upper ceiling on our focus. So we only focus on brackish water, and ideally anything from 3,000 ppm down. So in many cases, CapDI affords a very attractive alternative to a technology like RO. But we also have cases, and I'm going to go over one with you today, where we've worked very, very nicely in conjunction with RO to really turbocharge or supercharge its performance. So in some cases, it's just a better idea, a better technology, and in other cases, it's a nice complement. So I thought on the next page I'd spend 1 minute covering exactly how the technology operates. Because I mentioned early on we flip back and forth between a purification and a regeneration phase. So typically, VOLTEA will operate in the purification phase for about 110 seconds. And a good example of flow rate, for the purposes of demonstrating how these cycles work, is a 38 gallon per minute flow rate. So we'll operate at 38 gallons a minute flow rate for 110 seconds, and then we'll flip the polarity of the electrodes while simultaneously dropping the flow rate. And we'll drop the flow rate all the way down to about 5 gallons per minute for the next 90 seconds. So a total single cycle, meaning one purification phase and one regeneration phase, is about 200 seconds, 110 of it at 38 GPM and 90 of it at 5 GPM. So over the course of one cycle, we will have treated a total of 82 gallons of water with a water recovery as high, in this case, as 91%. And the system will continually flip back and forth between this purification and regen phase all day long, every day of the week, every week of the year. So if we go forward one page, just to kind of summarize it, I'm on the page titled Semi-Batch Mode of Operation, Continued. For all you engineers out there, I thought I'd just give one quick summary for you. But again, about a 200-second total operating window for purification and regeneration. Now, we're not always going to be able to get 91% water recovery. That's going to depend on what types of salts are in the water and what types of flow rates we need to operate at. But what this does give you is a very clear understanding of exactly how the technology works and switches back and forth between a purification and a regeneration cycle. If we can go forward one page, what we've seen, particularly over the last 2 years and 1 quarter, is about a 6.5-fold increase in the number of deployed systems and an over 11x increase in the number of deployed modules. Now, David hit on something in his introductory remarks that I wanted to come back to, and I want to comment on here. These are real-world systems. They're full-scale systems producing hundreds, thousands, or tens of thousands of gallons a day that were actually purchased by customers to solve problems for them in the real world. So these aren't R&D systems. These are real deployments. If we can go forward one page, I thought we'd walk through some examples. And I'm actually going to give you 7 different examples of real-world installations. The first being an automotive paint line rinse water reuse application. So I'm currently on page 12, and this is a case study overview for the first application we did in the automotive world. We've actually done 2 of these now. In all of these case studies, I'll give you a PFD across the top, and then I'll give you the actual performance data along the bottom. And what I'd like you to pay attention to for each of these is how incredibly simple the pre-filtration is. So there are at least 7 different steps along the process for building an automobile where it's painted. I'm not talking about the skin of the car. I'm talking about the chassis and other components internally. And in between each one of these steps, there has to be a rinse bath to prepare for the next paint step. So what we've done then is we've taken the water out of that paint line rinse bath. It goes into a tank before being run through a 3-micron filter and into one of our VOLTEA CapDI devices. Now, I'm going to give you several examples of reuse and recycling type deployments. In every one of these cases, there are myriad technologies out there to clean the water, filter the water, and do everything that you need to do to prepare it to use it again, except one thing. And that final thing is to efficiently get the salt out. And that's what we do. So in the automotive paint line, the water, after going through a 3-micron filter, goes into one of our capacitive deionization devices. We then tunably remove the remaining dissolved salts. And for this particular customer, they need purified water with a conductivity less than about 170 microsiemens per centimeter. And their desire was to have a recovery over 80%. In actual fact, that meant we needed to remove just over 85% of the salt, and that's exactly what we've been able to do. The total energy cost in this application is 0.96 kilowatt hours per cubic meter, and it's important to note that energy usage includes the feed pumps, the CapDI, the product forwarding pumps, and all associated treatment equipment. So any energy requirement data that I'm giving you is not just for the CapDI device itself. It's for the entire system, including feed and product forwarding pumps, etc. So this is the first case study, and we give you a lot of detailed information on the components that are in the sample water and the level of those remaining components after CapDI treatment. So if we go forward, I'd like to talk about a cooling tower application where CapDI is serving as a general deionization and a water softening technology for the makeup water. Very simply, the makeup water runs through a 5-mic filter cartridge before going into VOLTEA'S CapDI to remove the salinity on the way into the cooling tower. The lower the salt level going into the cooling tower, the higher the number of cycles of concentration you can get during cooling tower operation. In this particular case, we're treating canal water. So it's pretty impressive to think canal water is simply going through a 5-mic filter cartridge before going into the CapDI unit. That's all the pre-filtration that's required. And depending on the operating condition, so for 70% salt removal with a recovery target of 90%, we were able to operate at an energy consumption less than 0.6. But we also operate at a different setting where we're driving 80% salt removal and only 65% recovery. This demonstrates the very, very simple way that you can change the operating condition of the equipment depending on what the targeted water quality output is. One comment on cooling towers. This technology is profoundly effective for cooling towers so long as the cycles of concentration are less than 4. If the water going into a cooling tower happens to be in an area of the world where it's naturally soft and they're already able to get a cycle of concentration greater than 4, because of the way cooling towers work, you get very little benefit by using a softening technology like this on the feed. The other comment I'd make here is notice that we're not removing so much of the salt that the water becomes aggressive. So one of the reasons you don't see a lot of ROs deployed in cooling towers is because RO water can actually create a different problem where it's a bit aggressive for the equipment. So this is a cooling tower makeup water. Let's go forward one. This is an extremely interesting example where we actually treat the blowdown from a cooling tower. And so the cooling tower blowdown first runs into a granular activated carbon filter. There's a lot of constituents in blowdown water that don't exist in cooling tower feed water. After the granular activated carbon, it runs through a 3-micron filter and then into the CapDI for DESAL. And so again, in this case, you'll notice a couple different operating conditions. depending on what the client is trying to achieve specifically. In one case, the client wanted over 70% water recovery and only 40% salt removal. But in another case, they wanted to see if we could push the salt removal to 55% and still maintain water recovery at 70%. And it's a very simple matter of adjusting the operating parameters, and we've been able to deliver exactly that performance. Again, all at an energy consumption of less than 1 kilowatt hour per cube, including feed pumps, product forwarding pumps, and all of the associated equipment. Now, cooling tower blowdown water can certainly be treated, but if you have an application like this, we're definitely going to have to work with you because it depends upon the specific biocides that are used in the cooling tower. Our membranes and electrodes are very robust to many biocides and to many antiscalants that are used in cooling towers, but certain biocides and some antiscalants can become problematic and poison our membranes, and so we just need to work with you to understand what's used at your particular site. But treating cooling tower blowdown water for reuse has and is done by us in the real world. We go forward one case study. This was a very successful membrane bioreactor effluent treatment application where the customer actually ran our CapDI head-to-head with an RO, and the customer had some very clear targets. They wanted a 75% or better water recovery, and the salt removal needed to be a minimum of 65%. We operated for several months for this in the head-to-head comparison and then thereafter, but over several months of operation, VOLTEA was able to deliver approximately 72% salt removal and 73% water recovery on MBR effluent water. A key objective for this customer was energy cost had to be less than 1, and in actual fact, we operate at about 0.45 kilowatt hours per cubic meter, and in the head-to-head comparison with the RO simply wasn't able to get to that low of a level. If we go forward one page, an application that we're super excited about is horticulture. There is one error on this page. In the PFD, oh, it was great. Actually, I see it's fixed. Thank you. In the PFD, water going first goes through a 5-micron filter cartridge and then into the CapDI unit. Product water is for irrigation. And the idea, and I've just learned this in the last year, certain crops have a greater or lesser tolerance, particularly to the presence of sodium in the irrigation water. And so this particular client has long been able to grow tomatoes, but would also like to be able to grow peppers and other crops that have a sensitivity to sodium. And so the idea very simply is, can you change the amount of salt that you remove depending on the crop that we're irrigating? And so you see 4 different operating conditions here, ranging from a salt removal minimum of 78% all the way up to, water recovery minimum of 78% all the way up to 84%, and relatively low salt removal, but again, crop yield is critically dependent upon the sodium level in the irrigation water. And so what we're able to do then is we're able to tune the amount of sodium that we remove so that the irrigation water is suited to the crop and the farmer is able to maximize their crop yield. If we go forward, 2 final case studies. One's in commercial laundry, very similar to what was done in automotive. And what we do here is we take laundry wastewater. In the U.S., we've got a great partnership with a company by the name of AquaRecycle. AquaRecycle has a technology to do everything that you need to do to the water to get it ready to reuse it again, except one thing, which is to efficiently get the salts out. And so they've deployed our CapDI technology as the final step in their treatment process to take the salts out it turns out if you don't control the salt level and you run the water back into the commercial laundry, the linens will start to gray. And so it's a critically important step in the process, and we've got now multiple systems operating with our partner at Aqua Recycle, where, again, CapDI is used to tunably remove salt, making the water suitable to go back into the laundry process for reuse. And the final application or case study I wanted to talk about is also in commercial laundry, but it's not in reuse, it's actually on the makeup side. As you might imagine, commercial laundries are very large users of water. And so many commercial laundries operating around the planet, if not most or all, have very large water softeners. And certainly in the salt-ban regions of the U.S., Western Europe, and other places in the world, there's a real desire to have a viable technology to replace traditional salt-based water softeners. And we've certainly got installations in commercial laundry on a very large scale where we simply function as a water softener for the water as it first comes into the laundry. And having a lower salinity level allows for the detergents, the whiteners, the brighteners, and the fabric softeners to perform much, much better. But you don't want to remove so much of the salt that you actually create aggressive water. And so this is an example of taking advantage of our tunable removal to allow for no salt, no chemical softened feed water. And the final comment I wanted to make is related to cost structure improvements. Certainly in the last 2 years, the industry, academic researchers have been monitoring the cost structure of capacitive deionization because CapEx, as David said at the beginning of our discussion, is critically important. Just in the last 2 years alone, we've taken nearly 50% of the cost out of the system and over 60% of the cost out of our modules. And so this kind of pricing improvement is what is underpinning the very fast adoption in the industry of the technology. And hopefully what we're now seeing is the precipice of a transition from an emerging technology to a broadly accepted technology in the industry. With that, David, I'll conclude my remarks, and I sure hope we've got a lot of questions.
All right, thanks. So we're at the point of question and answers. And actually, it's going to be Bryan, of course, that's going to be answering all of your questions. So Bryan will first repeat. He'll be given a question. He'll repeat the question, and then he'll give the answer. So any questions that you have, please type into the question box if you haven't done it already. So Darryl, you want to start him on the questions?
Okay, so the first question that I see is this technology applied and economically viable for lakes, seawater, sewers? This is actually a really great question, and I'm going to take it in each piece. So for lakes, absolutely, and surface waters in general, particularly if you're in a part of the world where at certain times of the year the water temperature gets cold. One of the things we didn't talk about today is the energy cost to treat cold water with traditional membrane-based DESAL goes up considerably. Said differently, as the water temperature gets cold, the energy cost required to operate a traditional membrane-based, like an RO technology, goes up considerably. And that's not the case with CapDI. Our energy consumption requirement is relatively flat from a water temperature just above freezing all the way up to 60 degrees Celsius. And so for lakes, rivers, surface waters in general, it is viable, and in actual fact, we do have applications. If you look at our website, VOLTEA.com, you'll actually see a video for a steel mill in Lorain, Ohio, where we're taking water right out of the Black River. and we treated that water and make it suitable to feed into a cooling tower for a steel mill. So lakes are certainly viable. The same as for sewers. However, let me comment about sewer water. It would first have to be treated in some sort of waste treatment plant. So we provide a water quality requirement for feed water to our system right on our website. Raw sewage water cannot run into our system, but water leaving a well-operated wastewater treatment plant from a sewer, once that water is treated and it only needs the salinity to be removed, then we can certainly handle it. And for seawater, let me say, CapDI theoretically is very effective for seawater and higher salinity applications. VOLTEA has a strategic focus on brackish water. And so we only focus, as I mentioned during the talk, on waters where the salinity is no higher than 3 or maybe 4,000 ppm. However, VOLTEA has licensed our technology to a company out of California named Atlantis, and Atlantis does apply CapDI to higher salinity waters such as feed water. But VOLTEA'S application of our technology is only in brackish water. If you had a seawater application, we would certainly put you in touch with the company that we've licensed our membrane technology to in California. Okay, the next question. Does this membrane capture any valent ions like divalent, multivalent, microbial particles, and flourides? So I'm glad you asked. Divalent and multivalent ions actually come out slightly faster than monovalent ions. Let me specifically address it. So throughout the talk, I gave you 7 different real-world examples where we've applied the technology. And in all of those cases, customers have slightly different performance requirements with regard to how much salt they want to take out of the water. I always tell people, don't take any more salt out. Don't pay to take any more salt out of the water than what you need. So if 70% removal or 80% removal or 87.3% removal is good enough for your application, let's only take that amount of salt out. And if I set my overall salinity removal to, let's pick a number and say 70%, the overall salinity in the water is going to come down by 70%. But the divalent and the multivalent species in the water, take calcium and magnesium, so-called hard salts that are divalent, those are going to come out a little bit more than 70%, maybe 72, 73, or 74%. And so they do come out. Microbial particles, no. Our technology is not intended as a disinfection technology. Now, I appreciate that some microbes do carry a slight charge, and to that extent, there may be some removal. Our electrodes are also based on activated carbon, and of course, activated carbon is obviously going to have an affinity for organic type particles. Flourides will certainly come out of the water as well, so long as they're charged. The next question is it possible to use this technology to the treatment of sulfates from tailings of copper mines? And the answer to this question is absolutely. Again, any molecule that carries a charge will be removed. Now, what we may need to do is adjust the pH. So boron is a classic. WHO comes in and out of, it becomes a priority and then not a priority on the removal of boron. So we just change the pH of the water to ensure that an ion is in fact, or that a molecule is ionized, and once that's done, it will in fact be removed. Sulfates is a great example. Can you also use ozone to prevent fouling? Absolutely, and in actual fact, we do. We have systems that are operating where ozone is in front of our system, The ozone serves as an antimicrobial, but the ozone also serves to oxidize and digest low molecular weight organic molecules, and in so doing prevents fouling. The next question, will CapDI work on reuse water from a municipal waste treatment plant? Absolutely, and in actual fact, the example that we gave you, the case study we gave you, where CapDI was run head-to-head, that was a municipal wastewater treatment plant in Singapore. There are others, and it works famously well. We just want to make sure that the water quality coming out of the waste treatment plant going into the CapDI is suitable. Yeah, that application too. On page 15, the case study for MBR effluent treatment, that's actually on page 15, and that was a municipal waste treatment plant in Singapore. So it will absolutely work well there. Energy use of 0.96 kilowatt hours per cube, recovery 85%. Which actual absolute flow in liters per hour do you run? So that is one specific case. Let me flip back. I don't want anyone to leave this call believing that CapDI always runs at an energy consumption of 0.96 kilowatts per cube when the recovery is 85%. The energy consumption, we've got cases where energy consumption is less than 0.2 kilowatt hours a cube. So that was one specific example, and I'm just flipping back. To find it. Okay, I think you're looking at the cooling tower blowdown for reuse. No. The first one? The automotive paint line. Okay. Yep. So 85% removal, 85% recovery, and 0.96. The question is, what is the actual absolute flow, feed water in liters per hour that you run? I will actually, David, for a question like this where I don't have the answers right at my fingertips, can we flag this question and send out to all participants the answer? And what I'll do for whoever asked this question, we will answer for you the actual feed flow. We'll also answer for you the net pure flow. Because remember, feed flow versus net pure flow are two different things because of our system's constant switch back and forth between purify and regenerate. But if there's a way to flag this one, I just don't have liters per hour right off the top of my head for this example, David, but I would certainly like to get this, the direct answer for this questioner. If there's a way to do that, please.
Yes, yes, there is. So all of the question and answers, if we don't cover them here in the Q&A session, then they'll be handled by email.
Great, thank you. The next question is, what after the ionic membranes is saturated by deionization? I'm not sure I understand this question. I think what you're asking is what is behind the ionic membrane that becomes saturated. So the ionic exchange membrane is actually coated right onto our activated carbon electrode surface. And so ions that are able to pass through that membrane are actually trapped within that activated carbon electrode surface. What is the lifetime of one product? We've got, it completely depends on the application and how hard we're asked to run it, but we currently have products that have been in operation for over 3 years and are showing projected lifetimes exceeding 7.5 years. So it completely depends on the application, but we actually have several systems and modules that have been in operation for a few years now. We have a very accurate way of predicting lifetime, and even after more than 3 years of operation, we've got a statistically significant data set of modules that are showing lifetimes in excess of 7.5 years. And that's the module itself. The system, of course, has a 20-year lifetime, but I'm talking about the module itself. The next question is, I think that's it. think we're out of time, David.
All right, thank you so much. Really wanted to thank you, Bryan, for an excellent presentation with some really good data. I appreciate that a lot. And for more information, if you want to learn more about this and other membrane technologies, we actually have a 3-day course coming up here in just a week or two. And anything else that you need, we certainly would like to work with you. So thank you so much for attending. And as you exit, there are 3 polling questions that just ask you your level of satisfaction with today's webinar. So thanks again so much, and we hope to see you at the next webinar. Bye-bye.